All right, so I'm Fernando Peruani. I'm working at Cergy University. So before I used to be in Nice, and I want to thank the organizers of the program for the invitation and for the work they are doing to organize all this. So let me start. I mean, I have been doing different kind of stuff from in the past, mainly, well, anyway, so different things, and this is kind of a natural continuation with what I'm doing right now. And it's basically the following. In my group, what we try to do is we look at collective and individual behavior across scales, and that means we look at the behavior of from bacteria to sheep, and literally bacteria and sheep. And we try to look at how is the behavior of these guys individually, as well as if we manage to reproduce or find in the way they self-organize in order to form collective patterns. So why, I mean, basically what I'm telling you is that though we are not directly doing experiment, I would say we pay for the experiments, or we are funding experiments, and we are, I mean, we couldn't get lab space and so on, but anyway, so we try to do experiments in collaboration with colleagues. And what we mainly do is we try to propose mathematical models to describe these systems. And so why you need tools for understanding biological system mathematical models? I mean, this is my own way of looking at this. I think there are two reasons. One is to test biological hypotheses. The second is to provide mechanisms and proof of principles that are consistent with empirical data. And at least what we try to do is, if we got with, we have a model that reproduces the data, and it's reasonable, then what we will try to do, I mean, we will believe, that whatever we are doing, and then we will try to strip details from that model, making as simple as possible, in order to identify what you can call it the self-organizing principles behind the patterns that you are observing. So that is basically the philosophy behind what we do. So can we ask a question? Yeah, sure. So you assume there are self-organizing? Yes. Must be. I mean, let's say, if something happened, there should be some reason for that to happen. That is what I assume, that there is a mechanism of some sort. But it must be self-organizing. Oh, this is because the self-organizing principles is most of the stuff we were doing is on collective behavior. Not only, as I mentioned at the beginning, we are also looking at the individual behavior. But if you have something like this emerging in the spirit of phase transition and so on, then I would tend to assume that there is self-organizing principles. You can also respond to a chemical gradient or do many things which are externally driven, or it's not a result of interactions. Though in general, let's say my own interest is on self-organizing principles. I find it more interesting what emerge from these simple rules than when it is imposed by whatever boundaries or externally. All right, so so how to do that? So and how you can basically explain the behavior of bacteria or sheep and their collective behavior. What kind of model can you use? And what we have been doing for a while in the last years is to propose the following formalism. Theoretical framework, I put it here, that is the following. I will try to explain it. So we assume that we have a bunch of agents. The agents are going to be the individuals, that could be bacteria, sheep, or robots. And we are going to assume that these guys possess an internal structure, a mini brain, if you want, that I'm going to call it the internal control system. And up to now, what we have been assuming is that this internal control system is a Markov chain. It's a network connected nodes that basically controls the behavior of this individual in space. And I will try to convince you that you can do a lot of different things with that, and you can do mathematics as well with this kind of models or formalism. So this is the idea. Let me see if I should be here, right? So for the Zoom. Yeah. All right. Anyway, suppose that you have a trajectory of one individual. And now I'm going to forget about interaction with other individuals. And the trajectory of this individual is very peculiar. At the beginning, we see something like this, a spiral motion, then goes into this red stuff, a zigzag, and then this blue pattern kind of square thing. Doesn't matter exactly, but we need to identify different patterns. Here we have 3 patterns, motility patterns. And now what we will do is we will measure for how long the individual stays in each of them. So basically, how often you see the individual performing a spiral motion, zigzag, or this blue thing. Could be whatever you think of. Now, what we are going to do is we are going to try to build or find what should be the brain of our agent. And the brain of our agent is going to be a Markov chain. And now we are going to do the following. We are going to put several nodes in there. And if we are in one node that is black, we are going to behave, we are going to move in space in a spiral. If we move to a node that is red, we will start doing zigzag. And if we are in a blue, we do this other stuff here. So the color of the nodes tell you which equation of motion you have to use. And why is it the motif or the network that you need to use here? This one should be able to reproduce the time you stay, the distribution of time you stay in each of these patterns. And then the question is whether this is, if you can find a motif that reproduces all these or not. And okay, so it enters into the, if this is unique, right? This is the other question that you could ask. Okay, so same. Yes.
Is a priori knowledge of these patterns, like before?
No.
Or you have to identify them on the.
You have to identify, and I will try, and I will start by giving you the flavor of the framework model, if you want, and then we will try to apply it with one particular example that I will more or less detail, and I hope that will answer your question. Okay. So I said that these guys will choose things. So you use equation of motion. So if you do that, that means that you can have interactions in space that are classical interaction. You can have forces and you can have torque among these guys. So in physical space, but you have also this internal space, the space, within that brain, what happens within the nodes, and then they can interact also at that level. So, and this is basically what I'm to represent in here. So what could happen is one individual is in a given behavior, suppose is looking for predators around, but sees some other that is relaxed and eating. So this guy could say, well, that sounds a good idea. So I start eating right now. And so that means that they may synchronize their behavior. And that is something that will happen at the level, of internal state. They may synchronize their internal state. So there's 2 types of interactions in real space and in internal space. And of course, these rates in here may depend on how are the position of these individuals in space, and interactions in here may depend on the internal state. So all combinations are allowed and possible. So, all right. So now let me be, trying to go to being as concrete as possible. This is a very simple example, and this is how we started thinking about all this. Suppose that what you have is, this is our agent, and our agent moves in 1D. This is, you can do it in 2D and 3D if you go to the reference I'm giving you here. But imagine that just the simplest case is 1D. So your agent moves at velocity v0. The only thing that can do is moving with velocity v0 to the left or to the right. That's all. And that's it. That and it's going is moving through a chemical concentration C, and is able to measure only locally the concentration at different position where it is, whatever it is able to measure that concentration that is in there. This is this little arm here. So the equation of motion is going to be given by a Langevin equation like this one, where this is white noise, And this one is also a stochastic variable, it's S, and S can adopt only two values, -1 or +1. And there is transition from -1 to +1 and +1 to -1, right? So this is the kind of transition that can occur. But how they are going to occur? They are going to occur, I mean, given by this internal structure that I mentioned before. So the guy is going to have, I mean, in this representation, only two. I'm going to show you next that you can think of this rather expanding in four. And basically has an internal clock. Whenever you come across one, you change your moving direction, right? So you're moving to, let's say you are moving to the right. You go from two, then you come in one, and now you start moving to the left. You move to the left, and now you come here and you move to the right. So if you do that, I mean, what the advantage or why you would like to do that? Because if you look at the time between reversals, that if you don't do that, it's going to be, if you have only two states and an arrow that connect these two, I mean, if I'm plus moving to the right and I have the probability of rate to go to the left, that is going to be an exponential. And here we want, in order to fit the experiment, to have something that we can fit this kind of distribution. And in fact, the data I'm putting you here comes from Putida. So anyway, so this, we have used it already for some fun various examples, which I'm going to show you later. Okay, so now what you can do is, what I said to you at the very beginning is that the color of the node tell you which equation of motion you can use. So this equation, you can write it slightly differently. You can split this in two, and then you have the red equation and the blue equation. If you are in the red nodes, I mean, basically you use this equation. So here it's just a plus. And when you go to the blue ones, you just change your equation is change it only because of the minus. Of course, here, instead of putting this, you can put something way more complicated, an attraction to a given position that would be close to a resetting process. And here, you whatever else. So here is a very simple example, which hope that allows to illustrate the idea of this model. So now if you write things this way, you can do a bit of math. You can understand what happens in the system. You have to solve this set of equations. May look ugly, but you can deal with that. So you can get expressions for what is basically the drift. I mean, you can basically project everything to a particle that has a diffusion and a drift that depends on space. And these are the expressions for these two. And that you can do it in general for way more complicated networks okay, so in general, that's how it works, this format. So you go into this way of description, then you go through a system like this one that you can do it in 1D, 2D, 3D, whatever dimension that you want. And now you deal with the properties of the matrix of this alpha and beta and so on. So the structure that you end up having here, and you can compute drift, diffusion, and other quantities.
Sorry, question. You assume the psi is the internal noise, right? In the previous slide.
This
psi,
S?
psi.
Yeah, psi.
This is the corresponding to internal noise, right?
No, I mean, could be internal noise. This is a noise that is affecting the position, so that could be also thermal noise. I'm a bacterium and I'm subject to thermal noise. Or could be noise that is coming from the self-propelled engine, and if you want to put it at this level, that could also be.
Do you assume that psi and the fluctuating S are correlated in some way or completely independent?
No, they could be pretty much correlated. And in one example I'm going to show, I mean, we use explicitly that depends on which node you are subject to different noises. So that you can also, you can do almost.
So is there any difference between the red 1 state and the red 2 state?
These two, yeah, I mean, the difference is that this is your clock, let's say, your internal clock. But when you are in one in red, you're moving with this equation. When you are in one with blue, you're moving with this equation.
1 red and 2 red. 1 and 2.
Yes, if you are here, you are moving with this equation, and you are in this state. And when you move to 2, you keep on moving with this equation, and now you are.
Okay, my question is, what is the difference between state 1 and state 2?
that depends on the particular example that you're looking. This is just an internal
Because
state.
the motion is completely the same for state 1 and state.
Yes, it's
just
exactly
to get something that doesn't look like an exponential.
It's something that doesn't look an exponential, and these states, if you have, I mean, that could be something that you don't perceive externally, right? That could be I'm moving, and now I don't know, I'm afraid of a predator when I'm sure, whatever. I'm talking about the mathematical model, right? So I'm not giving at this point any interpretation to 1 and 2. Then I will give in the example of, I'm going to talk about bacteria, and then I will give interpretation to these states. But at this level, I don't care. And they have some internal state, and that would represent whatever. So that depends on the particular example that you're looking at. So this is what you can do. Something that you can use this model is, for example, we use it as a gradient to prove. In general, if you have something that is chemotactic, typically what you assume is that the bacterium, for example, is too small, so cannot measure a gradient directly, so can only get access to the concentration that is outside, right? So, but not really to the gradient. So what is the strategy? You measure here, you keep on walking in some direction, you measure again, and you compare your 2 measurements, and you may realize that you're moving up gradient or down gradient. And if you're moving up, up gradient, and you have a chemoattractant, you are happy, so you don't change your direction. If the contrary is happening, you change your direction, right? So you compare, you go along and you are comparing the gradient at different instants, and you have a memory curve. They show you that this way of thinking chemotaxis, at least mathematically, you don't need to do that. You can do it by just local measurement and without a memory kernel and so on. So which is, if you think about that, is quite strong statement. But okay, it's kind of abstract. Mathematically, you could do it. I don't know what bacteria does. Specific bacteria may do still the memory kernel and so on, but mathematically we know that it's not required. Okay, so now comes the next thing. So I'm going to use exactly the same idea, but this time, instead of controlling it, when I change direction, I'm going to control what is my speed. That is, if I'm in my queue, I'm, let's say, a red node, I'm moving. If I'm in a blue node, I'm not moving. My speed is 0. So I'm going to use to describe intermittent random motion. That's it. And that is going to be key because it's going to be one essential part of what I'm going to show you next, what is basically the behavior of Escherichia coli. All right, so, and you can generalize this stuff in this way. So this is the probability of finding your particular state M, assuming that you have M states. And then you have this Q. This is all the possible connection that you have in this network. And then you can look at the properties of this. And if you like to, this kind of stuff, you can look and read mainly this paper, where basically we put under which condition you can reduce it to an equation that has a drift and diffusion and so on. Anyway, so how to apply the proposed framework to real data. And now I go into being more concrete, how you make use of this idea. So here I'm showing you, this is Escherichia coli. I'm showing you one particular strain of Escherichia coli, which is called the enterhemorrhagic. So this one is called hemorrhagic diarrhea, and it's a serious pathogen. And what I'm want to show you is what happens when they don't perform addition to a surface. So we are going to look at the behavior of these guys close to a surface. So close to a surface, we are going to see, right, okay. So it's going to move in circles. Now, if I'm moving in circles, this moving in circles is because of hydrodynamic interaction, and that happens to all nutritious bacteria close to a surface. Near a surface, they move in circles because of hydrodynamics. Okay, so, but whenever I come close to a surface, I'm going to start moving in circles. That looks like a very inefficient way of exploring a surface. Imagine that over here, there is a cell that eukaryotic cells, for instance, this is an experiment that we have been looking, that this bacterium wants to infect. If you start moving in circles, you will never reach, or will take you a very long time to find this cell that is sitting there. And by the way, I mean, this we also know that that there is no chemotaxis that can be used by these bacteria to reach these cells. But this is anecdotal for the moment for us. So now when you look at E. coli on the surface, this is typically not what you observe. You may observe this for a while, but in general, what you observe is that they are going to perform these stop events that are going to be associated with additions event to the surface. And as you can see, as they do this, they basically break one circle. So you see the arc, stop here, and now manage to resume moving in some other direction, in some other circle, if you want. And by doing that, of course, they can explore in a way more efficient way space. But now, because they are stopping, what you can do is you can look at the speed as function of time of these guys. And if you look at that, this is what you see here. This is speed and this is time. You see that this speed takes, let's say here, large values. So because the bacterium is moving relatively fast, and then the speed goes down and then up again and so on. So this is basically telling you, that this switching behavior, let me say it like that. And now you can use, if you look at the histogram of speeds, takes this form. So you can take this local minimum to the finest threshold. And we are going to say that when it's below this threshold, is in a non-moving or slowly moving state. And when it's above that, it's in a fast moving state. So why we want to do that? Because we want to get the statistics of times that the bacterium is moving fast. This we call it the running times. So when it's above the threshold, and the stop times or slowly moving times when it's below this threshold. This is this TOES thing. So, and now I'm showing you the distributions of this, in cumulative distribution of these times, and which is what you see here. This is the run times, and this is the distribution of stop times. Okay, so this is in log and this is in ln, and as you can see here, the run times straight line, the distribution of stop times is not straight line. That means this is an exponential, this is not an exponential. So let's go in how you can think of the problem. So I may say, I have two states. Either I'm not moving or moving very slowly, or I'm running, moving fast, right? So if you think that you have two states, you won't be able to describe this kind of behavior, because though you can, you will end up having an exponential for the distribution of run times, you will get the same for the distribution of stop time. Should be also a straight line, should be also an exponential. So that is not going to work. So what can you do here? You add basically you can add one state. You can add one state and see what happens. If you have one state, now you can describe also this kind of distribution and many others. And if we keep on enlarging that network, we will get more and more sophisticated distribution that we can eventually describe. Okay, here we can already do a good job with 3 states. And we know a bit more. We know that 2 of those states have to be associated with this stop time, so this stop regime. Nice, so we know that mathematically we need 3, but that was the question before. So which interpretation we give to these states? So these 0 and 1 need to be something, right? So they are with stop states, but now we want to distinguish when the bacterium is not moving, what's the difference between 0 and 1? And this is if you really want to get access to a given an interpretation. Otherwise, personally, I can't live without knowing what is 0 and 1.
Why do you need to stop the state?
Why you need to? Because this distribution is not an exponential. In log ln, as you can see, this is not straight line, so this is not an exponential. If I go to the previous thing, I will get 2 straight lines, whatever slope you want, but will be straight lines in a log ln plot. So this is not what I see in the experiment, so I cannot do that. At least if I'm pretending to describe the data I have. So I need a 3 state, and 2 of them will have to be associated with this stop regime, right? So let's go to the experiment and take a look. So we started to look what happens when the bacterium stops, and when the bacterium stops, often what you observe is what I'm showing you here, is this. Stops, the center of mass doesn't move much, but it's rotating. All right, so if I go back, so this is some stops were not pretty much stopped. Something was happening there, So the guy is rotating around. And now something important, you should not, the size of a bacterium, if of the order of 1 micrometer, from 1 to 2 micrometers. The rotations I showed you before were pretty large, right? So this is of order 20, this bar, 20 micrometers. So this is not the same. So this is also rotating, but this one is rotating without displacement almost of the center of mass, right? All right, so now we can do the following. We are going to say when the bacteria is moving fast, I mean, the speed was above the threshold, we are going to say that this is state 2 and it's running. When it's in this state, rotating, we say that it's in state 1. And when it's stopped, no motion, no rotation, no nothing, we say this is state is in 0. Now we can go back to the experiments and we can compute for how long we saw the bacterium in state 0, how long we saw it in state 1 and 2. So this is what I'm showing you here. This is again cumulative, and what you see is the time was in each of them. And also something important is each of them, the distribution is exponential. The distribution is exponential, and we can get the average value in each of these states. And now you can do more. You can say, okay, now I can compute for how often we saw a transition from 0 to 1 and from 0 to 2, from 1 to 0, and 1 to 2, and so on. And if you have all this information, now you can get all the rates, and that's it. Now you have your model. So you can describe exactly the data I showed you before, and you have access to all the arrows, the rate associated, all the arrows. Yes.
So before you use a threshold to distinguish between the 2 states, and how you distinguish between the 2 now inside the stall.
Oh, when I mean, this stuff,
Yeah,
basically is
like looking at where they actually stop.
when the velocity was low and we were observing rotation of this size of the bacterium. So you see that there's a I mean, this is you go and so you can see that this is not so difficult to distinguish, right? So you go, you are not going the center of mass much, and you're observing a rotation.
But that's the stop.
That's stop. I mean, stop is.
But there
yes.
are 2 things with inside the stop.
Yes, 0 and 1. I mean, 0 is you don't move at all. Then if you go in the signal, you will see something. I mean, if I see here, I'm saying stop.
Yes.
Like this, so means that I'm below this threshold. I'm
Right.
below this threshold, but the guy may be moving a bit, and the center of mass is moving. It's rotating, tiny bit. So
there are times when it's rotating, times when it's not doing anything at all.
no, this is like there. I mean, it's a boring movie, right? And then continues. But yes, there are movies of that. I mean, okay, so. And okay, so now you have this. What you want to do is something that one could do is now you feed it to the equation of motion. I would say that at the beginning. Now you want that information to describe the motion in space. And so here I'm showing you that you can think of, if I have 3 states, 3 equations of motion. The one corresponds to 0 to 1 and 2. This is described in a more compact way in this way, where this function v depends on which is your state q, or if you are in I is 0, 1, or 2. And this d as well. There was a question about the d as well. So now that you have had that, so basically you have a model that can describe what happens with the bacterium in space, which was with the brain was what I showed you before, where the network, and now with this network we are using it to control the equation of motion, I mean the displacement in space of this individual. Now you can switch to a description in terms of probability. This is probability you are in position X with the orientation theta, moving in that direction, time t, and that your internal state, you're in a node I in that mini brain. Okay, so you can do the math, you will get this kind of equations, and you can end up having your diffusion coefficient. Now, what is interesting, if you look at the diffusion coefficient, is that now you can see how it depends of the different parameters. As you can see, this is a nonlinear function of with respect to this transition rate, the 2, 0. This is from 2 to 0. This is the one that is controlling for how long I'm moving. And you can see that peaks at a given value. So there are two extremes that are easy to understand, which are, I mean, basically this value and this value. This value means I basically, whenever I go to 2, I immediately go back to 0. 0 was no motion. That means your diffusion coefficient has to be very low because you basically barely move. And now you have the other extreme, that is this one, which means your transition rate goes to 0, meaning that you are trapped in 2, and then you are moving in circles, and you are, I mean, because there is some noise acting on you, so that there will be diffusive, but with the diffusion coefficient that is very low. So at some point has this peak. The beauty is that what is interesting to realize that in experiment, these guys are basically using the rate that maximizes this the diffusion coefficient, which makes sense, right? Because this is the way they could explore in a more efficient way the surface. Okay, so yeah.
In this case, the bacteria only rotates clockwise. Does it make any difference?
I mean, bacteria on surfaces, they are supposed to be chiral, and they rotate always in the same direction. The reason is the lateral bundle is chiral and rotates always in the same direction. So when you put close to the surface, you will end up having rotation always in one direction. You can also extend it to something that rotates, I mean, without being chiral, but that would be a different model and not for bacteria. All right, so now I mean, next week I will be talking about sheep. So, but in sheep basically happens the same. We use also a model with 3 states in order these states have different interpretation. This is grazing, one is running, and the other is not moving with the head up. I mean, also sheep, basically this is the speed as function of time. This is for individual one, and as you see, it's basically not moving, suddenly moves, again, it's not moving, moves, and so on. And you can basically go and use the same machinery to understand what happens in sheep. I'm going to talk about that on Thursday, so I'm not going to spend much time today on these. And in sheep, something that happens is that they are a bit more sophisticated than bacteria, and what they do is they do it together. So they are, let's say, grazing together, and then suddenly there is a collective displacement. Everybody decides to move, and they do it all together. So that means there is a kind of decision making that they occurs there, and that decision making can be also mathematically described with the same formalism I show you. Okay, so now I can start my talk. No, I mean, this is, should I stop? Okay. Now, I will tell you a bit the idea. This is, I saw that there is the Reinhardt R1, so probably you know them. These are 2 guys from Los Alamos that have been working on a similar problem, and I will tell you the difference between what they have been doing and I have been doing. Okay, I will tell you this story in 5 minutes. Okay, whatever. So what means quench disorder in here? Quench disorder means, I don't know if you manage to see much. These things here are cells, eukaryotic cells, human eukaryotic cells, in fact, and the guys moving around, these guys are bacteria, are salmonella. So they are, this object, I'm going to consider that quench disorder, meaning something that is in space that does not vary over time. They are always in the same position, and they are going to affect the motion of bacteria that are moving around. So hope that you see these are trajectories of bacteria, and they come, I mean, typically trajectory is interrupted, but if you see, they hit and collide and continue moving in some other direction. So this is what I'm going to consider like a bath, if you want, of active particles in the presence of quench disorder. And so now let me go into what we are interested in understanding, and it's basically shown in this cartoon. if I have a rod, a self-propelled rod, a bacterium, and moves and hits an obstacle, what is going to happen is during the collision is going, this equation typically are written in an overdamped regime, so collision is going to be a slow process. So I do this, I collide, and I will align, or I will experience torque, and in this case, I will move parallel to the surface, right? So basically, that means that a collision implies a torque and implies that my trajectory is going to be deviated away from the original path. So basically, this is what you see. So I mentioned before these other people, what we're doing is assuming that particles were spherical and torque was not present in a model. I think in general, torque is always present, maybe the object is elongated, but in general, you may consider. So if not, what you could consider is that the speed slows down whenever you collide, which is true, that is going to slow down. That is not going to be the major effect if there is a deviation. You can include that there is a slowdown of the speed, of the motion, and that is not going to change much the result I'm going to show you. So the model is very simple. You have a particle that moves at velocity v naught. So in the direction, we are in 2 dimensions, in this direction. So the moving direction is given by this angle theta I. So the evolution of theta I is very simple. It's this equation. This is white noise that is acting on this angle theta I. So if I don't have this H, basically I have simply a persistent random walker. And the H means that is this expression, but what tells you is that when you come close to an obstacle, you are going to experience a torque and you are going to get deviated. This is just details, but basically what happens is that I'm getting close to the obstacle and getting deviated away from my initial trajectory. So, this we did it in 2013, many years ago, and a few years after, around 16 or 17, in the group of Denis Barthelot, they started to do an experiment with Quinker rollers, and they started to look at this same problem, putting one particle in there, and basically they started to get very similar results to the ones I'm showing you that we basically obtain with this simple model. So what happens in here, you have particles moving around in a landscape of obstacles, which are this red stuff, and the particles are these black arrows, and as you can see, they spend most of the time in these areas. So now if you look in detail what happens in there, so they are moving like in a maze, if you want, so moving around, avoiding these obstacles, but they may enter into areas where they tend to rotate, and they will spend a very long time rotating in one of those spots in there. Eventually, because noise, there is also dynamic noise there, they may move away from there and start exploring what happens around. So now you can try, basically this orbit, these areas are stable orbits that are found in a landscape of obstacles. But of course, because there is noise, they will be able to escape away from these traps. Okay, so
it's a bit restricted to the presence of
yes, this is strictly rotated to the present of the obstacle. Otherwise, these guys move straight ahead, except for some noise, so it will be a persistent random walker, that's all. So, okay, so you can do math here and do some calculations, but since this has to go fast, so I skip all that. You get a diffusion coefficient that goes in a non-monotonic way with the density of obstacles. Perhaps what I could mention is that you can try to do statistics on the time they spend in these areas. And basically, they stay in this area for a very long time. They move around till they find another trap. And now you can try to realize which kind of motion you have in there. And it turns out that the time they spend in these traps scales. The average value of the time in there increases logarithmically with the observation time. So if the
rotation equally clockwise and anti-clockwise in this trap?
That depends for which gate you enter. You understand? Because I can enter from So this basically leads to subdiffusion because you're going to turn apparently that is asymptotic subdiffusion. We can discuss how true is that. But at least for, let's say, most, I mean, numerically will be impossible to show that it is not.
There is no noise in the mix, no?
What?
There is no noise in mix.
In the position. No, we didn't put, now we have done that also, including noise in the air. I mean, doesn't, we did.
Anything changes?
No. I mean, this picture remains the same. Okay, so this is more stuff. So now you can add interactions between the particles, and this is going to be pretty much a Big-Shaped model. So particles moving around, but the difference is the same equation as before. This is what we had before, this and this part, and now we are adding this term that is interactions with other particles. And this is an interaction where basically what favors particles moving in the same direction. So they will align the velocity. This is called the Big-Shaped model in the active matter community. We call it Big-Shaped model, and particles move in the same direction. So this is kind of locally XY model or flying spins, what you have in there. All right, so in having this, what now we want to see the effect of having these obstacles. What you could see is in absence of obstacles, this is the order parameter, the magnetization of the system or the average velocity. This is when noise is zero. This is the highest values that you can get. And if noise is very strong, the system will be disordered, and at some point particles will start flying together, right? So and then you have this critical point and a phase transition taking place there. But if you add obstacles in there, immediately you see that this goes up and then down. And then you can prove that these points in there will go down to zero. And that is telling you that there is a noise that maximizes collective motion in the presence of obstacles. And there is a bit more. I mean, the reason for that, I will show you in a second. So when you are around here, they move away from these obstacles, but the clouds of particles coming, they will quickly reconnect. I mean, but when you are in this other region, so noise is very low, they go in densely, I mean, they are densely packed, so the clusters are very dense, and whenever they collide an obstacle, they split into and so on, and they get decorrelated, and order drops. And if you go into that direction, you can prove that the order that emerges in the system is quasi-long range, which is what you expect in equilibrium, and it's not the long range that basically made active matter emerge. That was when in 1995, in two-dimension, Big-Shaped reported that this system exhibits long-range order. So put obstacles, long-range order story is gone. So bands also get destroyed that are in there, and this is basically the summary of this part. And I think I should stop in here because it's 45 minutes. I mean, I will tell you what we did. We did that with topological interaction, and then we generalized this model with Igor Aronson to prove that if the system is, again, more mathematically, if the structure of the system is dissipative, you can prove that the motion is going to be of diffusive type, and if it's the Hamiltonian structures, it's non-dissipative, and when it's dissipative, trapping occurs, and this kind of stuff. Okay, thank you.
Question, comment?
I like this very much.
Okay, thank you.
Regarding the first part, where you explained how the coli could have these internal states, internal Markov chain of states, controlling how they behave. I cannot avoid trying to imagine how this could be implemented in a thing that doesn't have a central nervous system. Because in higher animals, the Markov chain of internal state can happen in the nervous system. Do you have any thoughts about how could this work physically in bacteria?
We have trying to look at that. We think that there's, I mean, you have the receptors measuring whatever, right? So I mean, I'm thinking rather in the first part that was on the chemotactic, where it is that is more or less understood. There is more literature and more knowledge on how that works is better than this tops is very new. So in the other part, what you can see is that there is you have a production of different molecules in there, and you have this thing that as you go above a threshold, you have checkpoints, let's say, right? So you
imagine it will be a change of chemical reaction.
yes, I mean, it will not be discrete, which is a simplification of the process, right, but something that you have production of some protein that above a given threshold, you switch into something else. I mean, this is what. Yes, that is really metabolic, and I mean, doing the work of going into all these details and this discrete stuff, I think is complicated. I mean, that was beyond what we were. I mean, this is pretty much, yeah.
Well, I actually wanted to add to this. So I don't know, just in case you would be potentially interested, because we're working a little bit on this. If you have any kind of intracellular signaling, whatever that would be, because the way I understand it is that you have sort of a multi-stable system because you have different states and you can change. So actually, what we're doing is we developed a method where you can quantify these rating times between switches.
Okay.
So if you would be, so this is pretty much going at the same thing. You have a system, and if you write it down, for example, as the ordinance whatever, you can actually see that, for example, you're bistable, whatever. So one can quantify the times you would wait between switching the states, and then that would be the system that Fernando was kind of explaining, just omitting the path you would do between the states. So
yeah. I mean, in the bacteriums now we are working with Marta and I mean Eric Lehmann that is in the system, for example, that is basically the classical way of describing this is this, right? So, and if it's here, you can transition, and when it is here, the flagellar bundle goes in one direction. Let's say it's moving in the running state. The running state is controlling, and this is, you have molecules, you have a continuous start, and then you have the transition from one to the other. So yes, and if you go to a description that like this is running and stop. In our language, this is, we are going to pick up the rate that go, I mean, now we go into, and then the other arrow that, I mean, let's say that you put this you have and this you can do a mapping between the two. So certainly that you can do. I mean, what is not trivial is when if you have information about this kind of potential financial.
So you can get the well, if you know the reaction network, you can do the well.
Okay.
This is what I was saying. That's why how you can measure those times so that equivalent to the transition rate to go back and forth between the states. This is what I was saying.
Okay. Yeah.
So if you because if it's a metabolic system, eventually that's a network, no?
Yes, it's a network.
From those ones, you can get the well. You can estimate it.
Sure. Yes. I think in principle it can be done, and it's an interesting challenge. Let's say.
And we could do without the brain.
Yeah.
Was there another question there? Someone?
I think so. The second half of the talk, I think we went a bit quite fast. So what was the biological or physical motivation to study this weak sect model? Disorder obstacle.
There's two things in here. So the motivation of what I saw at the beginning, I showed a system of cells and bacteria moving around. And in that problem, what we are trying to understand is how quickly a bacterium finds a cell, an infected cell, and how propagates from one cell, eukaryotic cell that can get bacteria inside, salmonella get inside, how many cells get infected with salmonella inside. So that was the motivation. But the reason for studying that in the district and so on was simply because I always imagine that this result by a long range was not very robust. And if you put the system in confinement basically we proved that you sneeze around that mole, and it's long range or it's on. So it's not robust that result. Though it's major result as a pillar of active matter, but yeah, I mean, whatever you do, except if the system is homogeneous, periodic boundary conditions, and so on, I mean, that was a theoretical motivation.
You started with the 2 states, and then based on the finding, you switched to the 3 states.
Yes.
And it worked well because they were all exponential, and you say, okay, 3 states, really, what is the limit? What if you could not fit? How many states you think you can?
Oh, you keep on expanding. And you go, you keep on expanding. You go pretty much in the spirit of hidden Markov chain. I think I would put it the other way. What can you not model with this kind of formalism or stuff? I don't know, but probably has limitations. Obviously, but no idea of how you. So it's pretty flexible. You can do a lot of different stuff, and then even you can,
What if you have power law?
You can even have a power law decay. So that is challenging, but you can have a very. I mean, I never said that was a limit of the number of states.
Okay.
So with that, and I do whatever.
Yeah.
So
when you have too many states, then it's better to go into a continuous description, no? I mean,
of course, I mean why the Markov chain and discrete? Because it was easy for us to prove to do some calculations. I mean, that goes. I mean, and it's closer. It's more intuitive, natural in some cases, but at least for the animals or the sheep and so on. But yes, but there is no profound reason to say it has to be discrete. That thing one could go eventually in something continuous. But if you have in something continuous, and now you have to deal with full complexity, and this is, I mean, this problem itself is already complicated. This one becomes much simpler, right? In my opinion. So now if you have in this, and now you plug with something else, that is the motion in space, now you have something that you can handle. Now you can do calculation. But if you have with the full complexity of the problem, in general, you get stuck. Yeah.
From a statistical point of view, I mean, I could fit in like instead of a hidden Markov model with these substates, I could do a hidden semi-Markov model with waiting times, right?
Sure.
Would that make a difference in how you model it? So is that?
I mean, the intention of using the Markov chain, I mean, was in fact avoiding going into the memory kernels or otherwise you can go into a neural theory and that kind of stuff, right? So which, if I don't have information about these states, I will need to do that. But I can always say, I mean, I do that because I don't have enough knowledge on how is the internal structure. I need to do, I mean, memory kernel. I mean, I would argue that way. Because you don't have enough information, you need to go to memory kernel and so on. But if you have enough, you have access to all that internal structure, everything is Markovian. Probably us, you can go with.
Sure, I'm thinking
what kind of.
Yeah, I'm thinking in terms of description of the system. I could go either way, right?
Yes, I mean,
but in terms of the mathematics.
Yes, I mean,
do you think this is easier?
I think it's easier, but it's true. You could invoke, and this doesn't preclude the presence of these. I mean, if I cut the part of the network and I say I don't have these 3 nodes or whatever, then you will need these. You will get these memory effects. Mm-hmm. That and then you could try to work with that, saying this is a unit where I need my memory kernel or whatever. So of course that's possible. Okay.
All set? Okay, thank you.